Hello friends, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 1 of a unit electrostatic potential and capacitance. So let's begin with the today's class. First, we will begin with the electrostatic potential. So what is electrostatic potential? We can define it at that electrostatic potential at any point in an electrostatic field. It is the work done in bringing a unit positive charge. Always remember this word, a unit positive charge from infinity to that point. I repeat, it's an work done in bringing a unit positive charge from infinite to that particular point. Okay. Now, what is electrostatic potential? We can say that it is a degree of electrification of a body. That means higher a potential, higher is the electrification of a body. Whether it is a scalar or vector, yes, it is a scalar quantity. You might have studied this in class 10 also. Yes, definitely it was a very introductory level, but it was there. And from there only you switch to the Ohm's law, which is V is equals to IR. Yes. So uh, let's come back to the potential. We can say one more thing. Electrostatic potential is a physical quantity which determines the flow of a charge from one body to another. That means, let's say this is a one charge, this is another charge. This is at potential V1, this is at potential V2. And let's assume that potential 1 is greater than potential 2. Then charge will flow from this Q1 to the Q2. Then charge will flow from this Q1 to Q2. So it always determines that charge will be flowing or charge would be flowing from which body to which body. It is also a degree of electrification and it is a scalar quantity. So whatever we know, let's derive a formula of it. It is a numerically equal to a work done or electrostatic potential energy per unit charge. So this is V is equals to work done divided by charge. As well as I can say so it's a potential energy divided by charge. And the unit of potential is joule per coulomb. Yes, we can say it as in volt also. A dimensional formula you can derive it. This is joule, unit of an energy. If I write a unit of it, it's in kg meter square per second. Coulomb, it is an IT, it's an ampere into second. So if you solve this, you will have this. It's an M1 L2 T minus 3 A to the power minus 1. So are you done with this? What we know is we know the definition of potential and we know basically it is in work done divided by unit charge. Always take a unit charge, yes, or rather we can say it's a ratio of the potential energy to a unit charge. Okay, so let's understand what is potential difference. What I can say is, let's say that we have done is already in previous slides. Again we are doing this is at V1, this is at V2. And let's say one of the test positive charge is there. One of the test positive charge is there. And you need to transfer this test charge from this location to this location. Then we can say that potential difference between any 2 points in an electrostatic field is defined as the work done to transfer a unit positive, always a positive charge, from one point to another, or difference of electrostatic potential energy between the points per unit positive charge. So what we can say is that if you want to transfer this plus Q charge from location V1 to a location V2, then it will not be happen by itself. I need to apply certain kind of work on it. So whatever the work I need to do to transfer a unit base charge from Q1 charge to the Q2 charge. That work done divided by that unit positive charge. It's in potential. The same thing I can write as in it's in difference in potential energy to the unit test charge. is known as the potential difference. We always have a more significance over a potential difference rather than potential, because potential difference ease of use of it, potential barely use of it. So we always interested, or I can say we are much interested in potential difference as compared to the potential. Okay, so let's move to the next and let's just find it out, that electric potential due to a point charge. I am sure that you must have go through this derivation at your school classes, but let's just revise it very quickly. So, what would be the electrostatic potential due to a point charge? Let's begin. Let's say you have this charge, a positive charge, and the charge is small q, and you require an electrostatic potential at point P. And this charge is at a distance of x distance from a point charge q. So q be the point charge and P be the point of an observation, and let a unit positive charge plus 1 coulomb be placed at a point P in its electrical field. That I know, that when we need to find out the force on something, yes, that force would be always equals to Q into E. So while I do this, I always put a unit positive test charge at a location where I require an electric field, and we are going to do the same thing. So let's begin with this. First, find out the electrostatic force between the point charge and unit charge. What was the force was? We always say it's in K multiplied by first charge multiplied by second charge divided by square of the distance between this. So it is an F is equals to K Q1 Q2 divided by X square. So what I can write is F is equals to K multiplied by Q multiplied by 1 divided by X square. So this is F is equals to 1 upon 4 pi epsilon naught into Q by X square. Now let's say, suppose a charge is here, and I am going to displace it by certain distance dx. You can move it this side or you can move it this side. According to that, direction of work done would be decided. But both, but one of them can be done. So let's say I'm going to shift it by by an element of length, that is dx. So whatever the work done I need to do, it is dw is equals to minus of f dx, because this is I am doing against the field, and as I am moving the charge against the field, I am doing a negative work done. I hope this is clear to you. If force is in this direction and displacement is in this direction, this is what we call as a negative of work done. So that's why I put up a minus f here. Let's integrate this. So this is dw2 integration of f dx. So what is f? It is a kq by x square, and I need to integrate it from infinite to location r. Why infinite to r? Do you remember the definition of potential? Do you? What does it say? What does it say? Yes, it says that it is a work done required to bring a charge from infinite to a particular point. That's why I integrate this from an infinite to r. Are you clear with this? Are you? Any difficulties? Is there? So let's move in. So if I integrate this, I'm going to integrate this x to the power minus 2, and my limits are the infinite to r. So at the end, what I can have is 1 upon 4 pi epsilon naught into q by r. Now, according to the definition, this is the potential. This is the potential at distance r from point charge. So what I know is that the potential due to point charge would be equals to k multiplied by that charge divided by this distance from charge to that point. It is a v is equals to kq by r. Yes, it is the potential at that point. It's a kq by r. Please do remember this formula. This will help us. Now, let's assume that there are so many potentials, there are so many charges, and due to this charges, you require a potential at a certain point P. Let's say you have a charge Q1, you have a charge Q2, you have a charge Q3, and so on. You have, let us suppose, a charge of Qn, and their separation respectively are the position vectors are R1, R2, R3, and Rn and onwards. And you require a potential at point P. Now, what can you do? You know that potential is a scalar quantity, yes? And when it is a scalar quantity, you just need to simply add it. So, let's add this potential at a point P. So, net potential would be equals to addition of all this V1 plus V2 plus V3 plus V4 up to Vn. So, if I make an addition of this, I can have a K Q1 by R1 plus K Q2 by R2 plus K Q3 by R3 and onwards. So if I write a generalized term, it would be a V is equals to K multiplied by sigma Qi by Ri, while I will be beginning from the 1 and ending from the n. This would be the relation. So this is potential due to point charge. So up till now, one thing should be very clear to your mind is, let's say this is charge Q and this is the point P where potential is required, and the separation is R. So that should be is equals to V is equals to KQ divided by R. Yes. And if multiple charges are there, if more than one charges or more than two charges are there, what you need to do is you need to simply add it. Yes, a very good thing is it is a scalar quantity, so you don't need to bother about the what would be the direction, whether it will attract or whether it will repel, and what happened and what would be the angle between them, and all that kind of stuff is not required because this is a scalar quantity. I hope those things are clear. Is it? So let's begin with the numericals. Let's move on. Suppose 4 coulomb of charge is there. This is point P and this distance is x. What they have asked is find out potential at point P. When and when we say potential, at this point of time we know only one potential. It is an electrical potential or it is an electrostatic potential. So we are always doing the same thing. Yes. So what would be its potential P at point P? What is the amount of charge? It's a 4 coulomb. So what I can write is my generalized statement is V is equals to KQ divided by R. Yes, K multiplied by charge itself divided by R. R is the separation, it's an X. It follows. You can replace this by 1 upon 4 pi epsilon naught into 4 by X, and it could be a 1 by X pi epsilon naught because this force will be a pi. Again, unit would be a volt. Unit would be a volt. Yes, easy, very easy. So let's increase the difficulty level and move on. Let's do it. Let's say this is the one of the charge. It's a 4 coulomb. This is one of the charge. It's a minus of 6 coulomb. This is, let's say, 10 meter. This is the midpoint. So this should be a 5 meter. And again, this should be a 5 meter. You have been asked that find out potential at point P. What can you do? Here, this is the potential. This is the potential due to multiple charge. So what you need to do is you need to find out the potential due to each individual. So let's give them a number. Suppose this is one, this is first charge, this is second charge. And when I consider this two charges, the potential due to first charge would be equals to K Q1 divided by R, or I can write as an R1. So this is equals to K multiplied by 4 divided by 5, and potential due to second charge, it is a K Q2 divided by R2. So that should be is equals to K multiplied by minus of 6 divided by 5. So net potential is V1 plus V2. Yes, it is a scalar quantity. So you don't bother about that minus 6 coulomb of whether it would attract or whether it would repel and what would be the angle and that all kind of stuff. Yes, you simply need to add this. So this is equals to 4K by 5 minus of 6K by 5, and the term will remain it is in minus of 2K by 5. This is voltage or joule per coulomb. So 4K minus 6K by 5. Yes, if option permits, you can replace the with the K by 9 into 10 to the power 9 or 1 upon 4 pi epsilon naught, that you need to replace according to the options given. Are you done with this? Are you sure? Are you sure? Ready to move next question? So let's move on. Suppose a square is given, and on this a charge has been placed, that is plus q plus q plus q plus q, and separation between two charges is A. Now this is the midpoint, and here it is point P. You have been asked that find potential at point P. Do it. Do it yourself. You must have your pen and paper with you, and you must start doing it. Do fast. Shall I help you? Let's begin. First, let's say this is distance x. So this all distances are x itself. Yes. And let's give them a number. 1, 2, 3, 4. Yes. When I give them a number, that potential V1, what it would be, it's an K multiplied by charge. Charge is Q divided by distance. It's an X. What is V2? Yes, it is same. It's a K multiplied by charge divided by X. What is V3? Again, it is the same. It's an K multiplied by Q divided by X. What is V4? Yes, this all are the same. So when I assume that V net, when I assume the V net, I can have a conclusion that it is a 4kq divided by x. Now what is x? Let's look. This is a, this is a. So this complete would be the diagonal, and it's a root 2a. This 2x would be equals to root 2 that you know, and x would be is equals to root of 2 divided by 2 into a. So this is equals to a by root 2. So what I can write is 4 multiplied by k multiplied by q divided by x. And x would be a multiplied by root 2. So this is equals to 4 root 2 multiplied by k multiplied by q divided by a whole. This is v net. This should be the v net. Yes. Now, now, shall I add something to this? Shall I? If I have been asked, if I have been asked electric field at point P, then what should be your answer? I am writing the question here. You are going to do it on your own. Find electric field at point P. This is your task. You must know this. I hope you know this very well. So let's move to the next question. Let's say this is plus Q, this is minus Q, this is plus Q, this is minus Q. And at this point, their separations are A, this is point B, and you have been asked that find potential at point P. What can you do? Yes, give them a numbers first. Let's say this is first, second, third, fourth. Now, yes, I need to write down the value of it. Let's say this distances are x. So v1 would be equals to k multiplied by q divided by x. You know this that all distances would be unequal. So no need to write it everywhere. We understand by this. So this is v1 is equals to kq by x. What would be the v2? Yes, v2 would be the same. Now what would be the v3? What would be the v3? Yes, this is of minus of charge. This should be the value of v3 because it is positive. What would be the value of v2 and v4? Yes, it is a minus of kq. This is value of v4 because these two are the positive one. Now v2 and v3 is a minus of kq by x. This is v2 and this is v3. Now what would be the v net? So when I find out the v net, I need to simply add this v1 plus v2 plus v3 plus v4. Yes, v1 plus v2 plus v3 plus v4. Yes. Now, if I add this, it's in k by x plus k q by x minus of k q by x minus of k q by x. So this is simply the 2kq by x minus of 2kq by x. And that would be the 0. So this is plus 2kq by x minus 2kq by x, and that comes to a 0. Now, now, as in the last as in the last slide, what we were supposed to do is, you are going to do the same thing. Find out electric field point P. Find out electric field at point P. Yes. So let's move to the next question. Let's move on. This is plus Q. This is plus Q. This is minus of Q. Again, this is minus of Q. The separation is, yes, this would be the situation. And at midpoint, a point P is there. At midpoint, point P is there. You have been asked that find electric potential at point P. You need to find out the electric potential at point P. What will you do? What can we do? Yes, give them a numbers. This is first, second, third, and fourth. Now write down the magnitude of this all. Write down the magnitude of this all. So let's say this separation would be the x, and it is same for everyone. So if I write v1, it would be a kq by x. If I write about the v3, it would be the same. It's an kq by x. If I write v2, if I write v2, it's a minus of kq by x. If I write v4, it would be the same. So now I require a v net. Now if I write the v net, it's a net potential. What should be the answer? It would be a kq by x plus kq by x minus of kq by x, again minus of kq by x. So this is equals to 2kq by x minus of 2kq by x, and this would be a 0 volt. What was your answer? What was it? And let me add the same thing to this question as well, that you need to find electric field at point P. Now tell me one thing, that have you find it out the electric field at point P in all three cases? If you have not, please do it very carefully. Take your time of 30 seconds. That can be done in 30 seconds. And what I want is that whether the answer of an electric field will be a zero or non-zero. That is all what I require. At this point of time, I don't require the magnitude of this electric field. But what I want is that I require that what should be the value of electric field. Do this very carefully. Do this and do this now. I require it. Do it. So as soon as you do it, let me just draw the situations of each cases. This is first case. Plus Q, plus Q, plus Q, plus Q. You do your work. You do your work and just find out the electric field at point P. Yes, this separations are the same that you know. Our second case was plus Q minus Q. Okay. And third case, yes, this was the situation. This is the situation. Now you need to find out that what would be the electric field at point P. Now in this case, in first case, you know that we have already find out the V net. We have already find out the V net. It is non-zero value. V net not equals to zero. What it would be? Then we must know that it is a 4kq by x. It is a 4kq by x. Now, what would be the electric field at point P? So let's look at this. I'm talking about the electric field. Please switch your mind from potential to field. It is a vector quantity. So when and when I need to find out the direction of that electric field, what I do? I simply put a unit positive trace charge over there and just try to find out the electric field. This is plus Q. Their separation would be the equal. It's an X only. All the charges having a separation of X. So what is the value of electric field at point P due to point charge? Have you remember it? Do you? Yes, it is a k multiplied by charge divided by square of the distance between these two. It's a k into q divided by x square. So when I write it's a k into q divided by x square. The, let's give me the number first. Again, 3, 4. So this is positive charge. This is also a positive charge. The direction of this is in this direction because it will rotate. It's equal. This is E4. This is E1. And this is E3. Yes. So all these four electric fields are in different directions, but they are in the same magnitude. So electric field at point P will be zero. So this is the first case where V net is not equals to zero, but electric field at point P would be equals to zero. Now let's look at the second question. That I have already found out the V naught and it would be a 0 because this is plus q, this is plus q. This is 2kq by x in positive and this is minus of 2kq by x in negative. So plus minus would be a 0. Yes. Now let's try to find out the electric field at point B. What was your answer? Is it 0 or non 0? What was it? Let's try to check it. This is plus q. So this will move in this direction. This is electric field. And this is minus q. Again, this will move in this. This is electric field equal to. This is plus 4. So this is 4. And this is negative charge. So it will open. This is open. So E net would be somewhere here. It could have a certain value, but it will not be everywhere. That means EB not equal to 0. So electric field is not equals to 0 in this case. Yes. Now let's move to the third and final case of yours. So first, second, third, fourth. What was the electric potential? What was it? Yes, we have to. This is plus Q plus Q. This is plus 2 kq max. This is minus. This is minus. This is minus of 2 kq max. And we need to be 0. Now let's try to find it out. Let's try to find it out for the electric field. So what would be the answer? Yes, this is plus Q. And this is point P. So this will move in this direction because it is going to repel it. It's in P1. Even this is positive. So even this will repel. So this would be in this direction. So this two will cancel out each other. This is minus of charge. As this is a minus of charge, this will attract. That's why this is the electric field that is here. And this is minus of charge. So this will move in this direction. This is electric field. So again, it will be zero. So what can you conclude? What can you conclude from this is a very, very important statement. Please look at this very carefully. Electric field. and potential can be zero or non-zero at any particular point P. We cannot directly comment on potential or electric field if we know value of either. This is what we know up till now. This is what we know up till now. Yes, we would be having a relation between potential and electric field in the next classes. And from that relation only, we can get some knowledge that yes, if this would be the value of a potential, this could be the electric field, or even a vice versa of them is same. But up till now, whatever we know up till now, we cannot comment on their status that if potential would be a zero, electric field must be a zero. If electric field must be a zero, then potential must be a zero. No, we cannot say like this because we have seen this. We have seen the cases where where net potential is non-zero but electric field is zero, where potential equals to zero but electric field is not equals to zero, and in third case they both were zero. They both were zero. Yes, even a one more cases can be created where net potential is not zero, even electric field is not zero. So so this kind of things can be done and we cannot have a directly comment on this. So I hope you understand with the what is potential first. Next, what is the electrostatic potential due to point charge and how it behaves and how it works. So let's shut it down from here. This is lecture number 1 of electrostatic potential and capacitance. When you meet to me in a next class, you must remember what is electrostatic potential of firstly and what would be its value if it is for the point charge. So let's shut it down. Thank you. Bye bye. Have a good day. Take care.